Hello one and all. This is Jyoti Petram from Modern College of Engineering, working as an assistant professor in Electrical Engineering department. In the last lecture, we have studied the topic from basic electrical engineering, that is single phase transformer, the basic definition of a transformer, then the classification of transformer and working principle of transformer we have studied in the last lecture. Now in this particular lecture, we will derive the EMF equation of a transformer. So let's see here. Introduction of transformer, the content of these slides, classification of transformers, construction of a transformer and working principle of a transformer. And here in this particular lecture we will derive the EMF equation of a transformer. So see here, this particular diagram, it will indicate an elementary transformer, that is the constructional details of an elementary transformer. Basically, this is nothing but the transformer core, basically made up of soft iron or different iron alloys or silicon material. So this particular transformer core, it will be consisting of two different windings on first and second limb. On the first limb, there is winding which is called as primary winding. It is highly inductive coil which is supplied with the AC voltage source, and on the another limb there is secondary winding which is also one of the highly inductive coil which is supplied from the load. So AC supply and AC electrical load, it is connected to respective primary and secondary winding of transformer. So here we will revise the operating principle of a transformer. Whenever the primary winding it is supplied with AC excitation, that time alternating current it will start flowing through the primary winding. Because of the alternating current which is flowing through the primary winding, and this winding is nothing but the highly inductive coil, it will create the magnetic flux surrounding to the coil. That is because of electromagnetism. Whenever a current carries a coil, the magnetic field or the magnetic flux it will get produced surrounding to the coil. That flux, it is nothing but the alternating flux. This particular flux, it will complete its path through this magnetic core. The dotted lines to this diagram, it will indicate the alternating magnetic flux which gets linked across the secondary winding, and this particular linkage of flux across the secondary, it will leads to EMF induce or EMF generation across the secondary of a transformer winding. So here in this particular diagram, the operating principle of a transformer can be explained very easily and in a simple manner. Whenever we will provide the AC excitation to the primary winding, because of the AC current flowing through the primary winding, the alternating magnetic flux gets produced across the primary, and some part of this flux gets linked with the secondary, which will leads to induced an EMF across the secondary winding. That is the simple operating principle of a transformer. Now see here, we will derive the EMF equation of a transformer now. So basically in five different steps we will derive the EMF equation. In first step, we have to write down the equation for instantaneous flux. Then we have to obtain the expression for induced voltages across primary and secondary winding respectively. And according to the EMF equation, and according to Faraday's law of electromagnetic induction, we will calculate the maximum value of induced EMF per turn. Then in fourth step we will obtain the RMS value of induced voltage per turn, and in the fifth step we will obtain the expression for induced voltages, that is E1 and E2. So step by step we will study how to derive the EMF equation. So let's see here. Whenever we will consider an alternating flux which will be produced across the primary. So see here, this is nothing but the flux waveform, that is variation of flux with respect to time. So here on x-axis we will represent the flux, and on y-axis there is time in seconds. So see here, the plus 5m and minus 5m, this indicates the positive and negative max value of the alternating flux which will be produced because of the alternating current flowing through the primary winding. So here this alternating flux, it can be represented by phi, it is equals to phi m sine omega t. See here, step 1, we have to write the equation for or the expression for instantaneous value of flux. Since flux it is produced due to the AC supply, phi it can be written as phi it is equals to phi m sine omega t, where phi m stands for maximum value of instantaneous flux, sine represents the sinusoidal shape of flux waveform, frequency f represents the frequency of flux waveform in hertz, and omega it is nothing but the angular velocity, which is nothing but the rate of change of angular displacement with respect to time. So angular velocity it is given by 2 pi into f radian per seconds. So this will be the equation 1 where we have written the expression for instantaneous flux. Okay. So now in second step we have to obtain the expression for induced voltage. So now according to Faraday's law of electromagnetic induction and according to Lenz's law, we have to write it down the expression for induced EMF across the primary winding as well as across the secondary winding. There is self-induced EMF and mutually induced EMF across primary and secondary windings that we have to mention here. So induced EMF due to varying flux is given by E it is equals to N into d phi upon dt, where N it is nothing but the number of turns of winding, d phi by dt it is nothing but the rate of change of flux with respect to time. And according to Lenz's law, whatever the value of EMF induced across the winding, it is always oppose its cause of production. So the minus sign it will be represented here. So E it is equals to minus N d phi by dt. So the cause of production of EMF it is nothing but the flux linkage, and it will oppose the flux linkage, that is induced EMF across the primary or secondary winding. It is E it is equals to minus N d phi by dt in volts according to Lenz's law. So this will be considered as equation number 2. So here we have written the expression for induced voltage according to Faraday's law of electromagnetic induction and according to Lenz's law. Okay. So now in step 3 we have to obtain the maximum value of induced EMF per turn. So per turn value we have to calculate, that is, so as to obtain the value of induced EMF per turn, substitute N it is equals to 1 in equation number 2. So this will be our equation number 2. Here we have to put the value of number of turns as 1. So what we will get, E it is equals to minus N d phi by dt. So N it is nothing but 1. So one number of turn we have considered here. E it is equals to minus of 1 d phi by dt volts. Therefore we can write the maximum value of induced EMF per turn as E it is equals to minus d phi by dt volts. This is considered as equation number 3. So now in step 4, so here in step 4 what we have to consider, whenever in this equation number 3 we have to put the equation number 1, that is phi value. Phi it is phi m sine omega t. So put the value of phi. So now substitute equation 1 in equation 3, that is the value of phi. What we will get now, E it is equals to minus d by dt of phi can be written as phi m sine omega t. It is in volts. Now phi m it is nothing but constant, we will take outside this derivation. So E it is equals to minus phi m d by dt of sine of omega t. So d by dt of sine of omega t, that is we have to take the derivative of sine of omega t with respect to t. So E it is minus phi m as it is, d by dt of sine of omega t is nothing but cos of omega t into omega. So E it is equals to what we will get, minus phi m into bracket cos of omega t into omega volts. So this is nothing but the equation of induced EMF per turn. Now we have to calculate the maximum value of induced EMF per turn. Now in this equation put cos of omega t as plus or minus 1. So cos of omega t it is equals to plus or minus 1, and omega, as we know, angular velocity omega it is given by 2 pi into f, that is radian per second. Therefore the maximum value of induced EMF per turn can be written as E max it is equals to omega into phi m, because cos of omega t it can be considered as, it is the value of cos of omega t is plus or minus 1. Therefore E max is omega into phi m. So omega here 2 pi f and phi m it is as it is. So E max it is equals to 2 pi f into phi m volts. Now see here in step 4 we have to obtain now the RMS value of induced EMF per turn. In step 3 we have obtained the induced EMF which is maximum value of induced EMF per turn. Now here we have to obtain the RMS value of induced EMF per turn. So we know the relation between RMS value and maximum value. RMS value it is max value by root 2, or RMS value it is equals to 0.707 into maximum value. Okay. So here we will obtain the RMS value of induced EMF per turn, which is equals to Emax by root 2. Emax is nothing but 2 pi f into phi m divided by root 2. So 2 can be written as root 2 into root 2, pi into f as it is into phi m as it is divided by root 2. So numerator root 2 and denominator root 2 gets cancelled. We will get RMS value of induced EMF per turn as root 2 into pi into f into phi m. Now root 2 into pi can be written as 4.44. So multiplication of these two, you will get 4.44. Therefore the RMS value of induced EMF per turn, it is equals to 4.44 F into phi m. So this is equation 4, where we have obtained the RMS value of induced EMF per turn. Okay. So now in step 5, we have to obtain the expressions for induced voltages E1 and E2. So what is E1 and E2? Here let E1, it is nothing but the RMS value of induced EMF in the primary winding with N1 number of turns, and E2 it is nothing but the RMS value of induced EMF in the secondary winding with N2 number of turns. So N1 and N2 are the number of turns of primary and secondary windings respectively. So now, so as to obtain the induced EMF, what we will consider here? Induced EMF across the primary winding can be found out by considering or by taking the product of RMS value of EMF per turn multiplied by number of turns of primary winding. Okay. So E1 it is equals to RMS value of induced EMF per turn is nothing but 4.44 F into phi m multiplied with number of turns of primary, which is nothing but N1. Okay. So E1 it is equals to 4.44 F into N1 into phi m volts. Okay. So equation number 5, it will give the RMS value of induced EMF across the primary winding. Now we will find out similarly the RMS value of induced EMF across the secondary winding, which is E2, which is equals to RMS value of induced EMF per turn multiplied by number of turns of secondary winding. Therefore E2 can be written as 4.44 F into phi m into number of turns of secondary are N2. Therefore E2 it is equals to 4.44 F into N2 into phi m volts. So equation number 5 and 6, it will give the value of induced EMF across primary and secondary winding. Now we can equate equation number 5 and 6. What we will get? E1 by E2 it is equals to 4.44 F N1 into phi m divided by 4.44 F N2 into phi 2. Or we can write this equation as E1 by E2 it is equals to N1 by N2 it is equals to K. This equation is known as turns ratio of transformer, and K it is called as transformation ratio of a transformer. So equation 5 and 6, these two are nothing but the EMF equation of transformer, that is the RMS value of induced EMF in the primary winding with N1 number of turns, and equation number 6, it will give the RMS value of induced EMF across the secondary winding. So in this way you have to derive the EMF equation of a transformer. Thank you.